I want to present an alternate version of the radioactive decay formula you'll see a lot. Um, we've been using the base 1/2 because it relates very, very naturally to the half-life. But it's more common to use the standard base E, mainly because when you get to calculus, it has some wonderful properties, and it's nice to sort of use that as a very standard base for everything as much as possible. And it's also, this relates really nicely to the doubling time video. So you'd probably want to watch that first so I can refer to that. Although this is technically self-contained. So here's the formula we've been using. If you have a certain amount of stuff, of radioactive substances decaying, and you want to know how much it is as a function of time, it's going to be however much it was at 0. We can just call that A of 0. It's analogous to the P in compound interest formula. There's various notations for it, times 1/2 to the t over L. And the idea there was you take t, you figure out how many half-lives that time is, and then you just multiply your sample by half that many times. And if this is a fraction, then you get some sort of funky power of 1/2, but that's okay. So we want to see, there's an alternate formula, which is A of t equals A of 0 still. That's never the interesting thing. Times E to the, now this is going to be times to the minus something because it's got to be decaying. If I did it to plus, then it would be increasing. And then that's going to be KT, okay? And so I claim that these can be made to be exactly the same. We just have to figure out how to choose K. And it must have something to do with the half-life, okay? So K is the rate constant. And you might notice that this is very, very similar to the PERT formula. Now that's for something that's growing, but it still has in the same slot the multiplier of t, okay? And that, of course, was the interest rate. So the rate constant for any kind of exponential growth or decay is just a generalization of the interest rate for continuous compounding. And so you should think about it in the same way and have the same intuition for it. Okay, so now, and that suggests, okay, this is expressed in terms of halving continually over and over again. This K is analogous to the interest rate. So if we have an idea of how doubling for an investment, a continuously compounded investment relates to the interest rate, that's probably going to be similar to how the K relates to the L. Okay, and indeed, that's what we're going to see. So we're just going to set these formulas equal to each other. Okay, A of 0 times 1/2 to the t over L equals A of 0 times e to the minus kt. Okay, this is supposed to be true no matter what A of 0 is and whatever t is. Well, the A of 0s cancel out anyway. They can't sort of fail. They can't screw it up because they just cancel. Okay. And it's supposed to be true for any t, but I need to isolate the L and the K to get the relationship there. Well, I'm going to take a logarithm. Okay, so I'm going to take the logarithm both sides. I could choose to take it to 1/2 base or e base or something else. I'm going to take it to the base e because that's the most standard thing. So I'm going to take the log of 1/2 to the t over L equals the log of e to the minus kt. Okay, on the right-hand side, those cancel out. That's the whole point of taking the log of something with an e base. And on the left-hand side, it's not going to completely cancel out, but I can use rules of log. So I've got log of an exponential expression. So I get the exponent, which is the quantity t over L, times the ln of 1/2. Maybe make it a fraction. Okay, well, I'm to show you how similar it is to the doubling time thing, I'm going to use one more rule of logs. Okay, that's the ln of 2 to the minus 1. Okay, and then that minus 1 also comes out. So you get minus t over L equals ln, or times ln 2. That should be equal minus kt. Okay, now the minuses go away. And that should be true for any time t. And the only way this number, ln2 over L times t, is going to be the number k times t is if those numbers, those coefficients are equal. And so, ta-da, we get k is ln2 over L. And there's our formula for the rate constant. And it's exactly, if we solve it for L in terms of k, multiply by L and divide by k, you get L is ln2 over k. This is exactly the same formula. It's the rule of 70 formula that related R, the interest rate, to the doubling time. And the cool thing is, it's the same formula even if you invert it. I probably should have mentioned that with the doubling time formula as well. If you have the half-life, divide it into ln2 to get the rate constant. If you have the rate constant, divide it into ln2 to get the half-life. Okay. So for growing investments, R has a certain relation to the doubling time, and for decaying things like radioactive decay, the rate constant K has the same relationship to the half-life. So quick example. If you have a half-life of, let's say, 3,000 years, what is the rate constant K if you want to express it with this natural exponential? K is just ln2, 0.6931 over 3,000, and that is equal to 2.31 times 10 to the minus 4. So we would express the formula for that substance as e to the minus, and you get, for half-lives, when they're long, you get some kind of annoying, tricky decimals here, times t. Okay, so this might look, I think it should look cumbersome compared to the 1/2 to the t over L formula. And for us, it is kind of cumbersome, but it's really, really good to be prepared to use E for everything in a later context. And so I wanted to show you that. And it's also cool that it's so closely, it's just the same formula as the doubling time stuff.